Hey there, in this video we're going to continue logarithmic differentiation. I wanted to just do an example of a problem where neither the general power rule or the exponential rules apply. And so just to review, right, the general power rule is that when x is the base, so if you have y equals x to the n, then the derivative is y prime equals n x to the n minus 1. Now here, right, we have x as the base, but notice that the exponent also has x in it, and so it looks like an exponential, but the exponential rule also does not apply here. The exponential rule says if you have y equals e to the kx, right, when the x is the exponent, then y prime is k times e to the kx, and if the base is something other than e, b to the kx, the derivative is k times b to the kx times the natural log of the base, not the exponent, the base. So here neither of these rules apply because we have x as the base, so it looks like a general power rule, but then x is also the exponent, so neither of this unfortunately applies. So what we're going to do is we're going to use logarithmic differentiation, meaning we're going to take the natural log of both sides. Natural log is a function, right? So that's why I do ln of both sides, because it's not multiplying. You're not multiplying just ln by itself. Natural log is a function. So once I do that, I'm going to have, so let me just rewrite my function over here. I have y equals x to the cotangent of x. So once I apply the natural log to both sides, I'm going to have the ln of y equals the natural log of x to the cotangent of x. Why do we apply the natural log? Because then we can use properties of logarithms and bring this exponent to the front, not because I'm taking the derivative, but by properties of logarithms. And that's the property that if you have x to the power natural log of x to the power of p, then you can write that as p to the natural log of x, or any base logarithm. And so now let's rewrite that. So I'm going to have the natural log of y is equal to then cotangent of x, my exponent brought to the front, times the natural log of x. And so this again just done by properties of logarithms. I have not taken a derivative, I just rewrote. Now I can take the derivative implicitly because y is a function of x, right? Here y is explicitly a function of x, y equals x to the cotangent of x, but once I write it this way, when I have ln of y, now I have a function of y, but y is a function of x, so this is really ln of f of x. So we're going to take the derivative implicitly. So on the left, the derivative ln of stuff is 1 over the stuff, so 1 over y times the stuff prime, so times y prime equals, and on the right I have cotangent of x times ln of x. So here I'm going to need to use the product rule. So it's important to recognize when you need to use those extra rules. So product rule says the derivative of the first, the derivative of cotangent is negative cosecant square x times the second left alone, so ln of x, plus the first left alone, so cotangent of x, times the derivative of natural log of x with respect to x, that's 1 over x. So that is our product rule, and now we simplify and solve for y prime. So meaning multiply both sides by y. To get rid of this y over here. So multiply both sides by y. I'm going to have y prime equals y times negative cosecant square ln x plus cotangent x over x. And now substitute back what y was. Y was, the original expression was x to the cotangent of x. and then I'm going to have negative cosecant x. If you don't like to write the negative term first, sometimes I do that. I don't like to have the negative term first. I'm going to write the positive term first. So cotangent x over x, and then minus cosecant square x, whoops, I forgot an x there, times ln of x. And that will be our final answer. All right, so that's one of those where neither the power rule, the general power rule, nor the exponential rule apply, because x is both in the base and in the exponent. And so then we have to use, this one definitely we have to use logarithmic differentiation. As you start doing more and more of these, you might notice that you always get essentially the exponential or the original expression back times, this is really the derivative of the exponent times the natural log of x. So that might be a shortcut, and you start to discover that as you do more and more of these. Okay? Contact me if you have any questions.